Good morning, Srini. Hope you have a good rest.
Yes, sir.
Ready to start?
Yes, sir.
Okay. Hope you put in an effort to study. If not, as I say, you won't see any progress. Yeah, wasting your parents' money for tuition. Right? It depends on you very much. You have to learn yourself. I can't learn for you. I cannot teach you. Put an effort. After I teach you, spend another hour, review through, and then do the question. What is happening now is after I teach you, you forget because you don't revise, you don't do homework. So there's no progress. So you keep on going that, your result will be the same as first term because you are literally not improving in your behavior. You are still coming for tuition hoping it will help you. It won't help you. Okay, let's start with Doppler effect. The last. Can you see? Yeah, what is happening?
I see a slide, sir.
Can you see the Doppler effect? Can see,
No, I can't see the image or something. I can just see a slide, the words only.
Can see Doppler effect,
No, I can only see a slide, the 21.5, and then some YouTube links. That's it.
Can't see anything. Cannot be, What is happening? Trying to figure out what is happening. What is happening? Okay, let's go to Doppler effect. What is happening? What's happening? Page 98. Syllabus 21.5. Describe Doppler effect for sound and use the derived formula. This is very unclear what they say. Do they want you to know how to derive, or they just want you to use the formula only? Okay, so very blur. The syllabus is very blur. You want a moving source or moving observer along the same line. Okay, so can see. Okay, what determines color in light? Yeah, what determines color in light? As you have said, color of light is determined by frequency or wavelength. So in sound is the pitch. Pitch is frequency of sound. Pitch and frequency are the same thing. Sound may be generally characterized by pitch, loudness, and quality. The perceived pitch of sound is just the ear's response to frequency, just like the eye respond to color. For most practical purposes, pitch is just frequency. Just take pitch as frequency. Okay, so that one summarized for you. What is Doppler effect? Either the source of sound or the observer is moving, or both of them. So this part, see shorter wavelength. Frequency of sound haven't changed, but see shorter wavelength. So what is Doppler effect? Refer to the apparent change in frequency. So this observer will hear a different frequency from what is given out by the fire engine. Of apparent change in frequency of sound when there is a relative motion between source of wave and observer. That means either the observer is moving away or towards the sound, or the source of sound is moving towards or away from the observer. That's what I mean by relative motion. Fire truck not moving, both A and B hear the same frequency. So B will see longer wavelength, right? And we use this formula. V is F lambda, longer wavelength, shorter frequency. When the ambulance approach you, the observer, you are the observer here, right? A police car approaching you. What happened to the sound? Right? First thing is loudness increase because the sound is nearer and nearer to you. Depends on your distance. Nearer to you, louder, further away, less loud. Pitch or frequency increases. Right? As you can picture the picture. Look at the picture, remember? Right? Just remember the picture. The shorter wavelength, higher frequency. Right? And as far as loudness is concerned, we look at intensity. Further distance, intensity smaller, so less loud. Nearer, intensity increase, so louder. Right? So for this observer, this girl, the police car is moving away. So you will hear, you will hear basically a sound of longer wavelength. Or loudness also start to decrease. Right? As the police car move away from her, the frequency will start decrease. So we can summarize that when the source or wave move relative to the stationary observer, there is a change in observed frequency. Right? And then you can use this formula to help us. V equals to F lambda. And also, okay, it's a constant speed. We are not interested in acceleration. Distance is speed times time, or in terms of formula, x equals to vt. Right? We have a moving source. We have an observer. So this observer, we start with both of them are stationary. Okay, so now memorize this equation and know how to use it. Speed of sound, v. It has not changed. Frequency of sound also not changed. It's given out by the source. S is the source. Right? If S is the source, and it is the speed of the source. F is the frequency of sound. O stands for observer or apparent change in frequency, if you like. Either observer or apparent change in frequency. So observed frequency or apparent frequency, speed of sound, V is speed of sound, F is frequency of source, Vs is speed of source. Negative when the source is moving towards observer. Right? You look at the two. Look at the speed of sound and look at the speed of the moving source. Sorry, the speed of sound and the speed of the source. If both are in the same direction, then you subtract. Right? Because you are looking at relative velocity, same direction, subtract. Observer, right? So if it's moving towards the observer, if the source of sound is moving towards the observer, we take it as negative because the observed frequency is going to be larger than the frequency of sound. Okay, so know how to use it. It's up to you already. I said to you, go back, try the homework, then you will force it in. Right? So remember this picture. Right? Let's derive it. Wavefront move from the point source. This is your point source. Right? Remember, the wavefront just join all the crust that is moving out. It's a point source, so the sound is moving out in all directions. So if that is your point source, right, can consider wavefront as joining all the wave crusts. Source of sound at the center emitting sound wave in all directions. This is the source of sound. Right? It emits there is a wavefront, right? Or the wavelength. That distance is the wavelength. So as the time passes, this one will move out. This one will expand to there, and then new one will take its place. Same, this one will expand as time goes on. So these are your wavefront. Right? This one will expand. This one will also expand to that one, right? Or move forward the wavefront, and new one will come out. Same, right? And repeat itself. T is a period of the sound source. Lambda is the wavelength or distance between the wavefront. And then we can use our lambda is V times T. T is the period. Or we can use F equals to V over lambda. Same thing. Either these two formula. Source is moving. Source of sound moving to the right. Wavefront is moving to the right. Right? Just now we have the source stationary. So the wavefront is the one that is moving out. But now we have the source of sound moving to the right. So the wavefront also follow the source of sound moving to the right. T, the period, time to travel is the same. Right? Frequency of the sound is still the same. Right? Keep that in mind. Frequency of sound doesn't change because it's from the source, but the observed frequency is the one, or the apparent frequency is the one that is changed. Right? The frequency and period constant. Apparent wavelength, that is your apparent wavelength or observed wavelength, is the distance between the wavefront. Right? So instead of using the speed of sound, now we have to modify it. Right? It's moving forward towards the observer, we subtract V minus V naught. That is the sorry, I tend to tend to confuse you. Let me just make a correction. Okay. That's supposed to be the source, not observer. Okay, so we use relative speed or relative velocity, where the source is moving and the speed of sound is moving. Remember, in this case, the speed of sound and the source are moving in the same direction. So we subtract relative velocity, we subtract. Right? Or same thing, V minus V naught divided by the original frequency. Right? So previously the wavefront doesn't move. The wavefront is the one that's moving, but now the source is moving, so the wavefront move a little bit more extra. Right? Same with the next one. As this one expands, next one will take its place. Right? So these are your wavefront. Same thing. Right? So the side that's moving towards the observer, the wavelength will decrease. The one away from the observer, wavelength will increase. That's important to know. Source moving towards observer, observer here shorter wavelength or C shorter wavelength. So you can either write as the relative velocity times your period, relative velocity divided by frequency. So the observed frequency is the speed of sound. Right? That one haven't changed. Divided by the observed frequency. Right? So we replace that observed frequency with this value. Okay, so at bottom becomes the top there. This one becomes the bottom there. Okay, so that is for the apparent or observed wavelength. Sorry, this apparent or observed frequency when the source of sound is moving towards the observer. Right? We are looking at stationary observer. Now we are looking at this person. Right? The source is moving away from him, from the observer. Source moving from observer, observer hears or see longer wavelength. Right? We call it observed or apparent wavelength. Same thing. Right? Wavelength equals to relative velocity. Right? Because both of them are moving. Both of them are moving. Remember, the source of sound is moving to the right. Sorry, the source of sound, the speed of sound is moving to the left, but the source of sound is moving to the right. Keep that in mind. Both of them are in opposite direction. That's why we add them up. Okay, times the period of the source has not changed, or the frequency has not changed. So same thing. We want to find the apparent frequency or observed frequency is just the speed of sound divided by the apparent wavelength. Then replace that lambda naught, this one, here. Okay. So that picture just summarize for you. Okay, that is your, you can try this already. Your worksheet number 15. Okay, now let's look at the source of sound that is stationary. Right? But the speed of sound is moving. Remember that. That means the wavefront is moving. This one, right? The observer is moving. Just now we look at the source of sound is moving. Now the source of sound is stationary. So the wavelength is constant, doesn't change. But the observer is moving. So he see the wavefront faster and faster. Right? Observer moving towards stationary source. That's your stationary source. You're observing moving. V naught. O for observer. Wavelength lambda is constant. Wavelength doesn't change because it's given by the source. So it's just the speed of sound divided by the frequency of the sound. But now, since both of them are moving towards each other, we add the speed of source relative to observer. Right? Cannot use the speed of sound anymore. You have to use the combined speed because both of them are moving. Sorry, the speed of sound is moving. Right? The wavefront is moving. The observer is moving. So towards each other. So we add them up. So now the observed frequency, the same thing. Frequency is the speed divided by wavelength. Wavelength haven't changed, but the speed is the one that is changed. So it's V plus V naught. Okay, so replace that wavelength there inside here. So we get this formula. Okay, anything that is not clear? Ken? Yep, Trini, are you sleeping? Okay, let's derive the other one. So when they are moving towards, the observed frequency is larger than the frequency of sound. Okay, and the observer, same thing, same as previously. Whether the observer is moving towards the source or the source is moving to the observer, you see higher frequency or shorter wavelength. Okay, observer is moving away from the stationary source. Now the observer is moving away. This one, the wavefront is moving towards the observer. Wavelength still constant. Wavefront does still stay constant. Right? Remember, the wavefront is the one that the observer will be seeing. But the wavefront is constant. The wavelength is constant. You can calculate it with the speed of sound, with the frequency of sound. But remember, the wavefront is moving and the observer is moving. So now we have to use the relative speed of source relative to observer. And the observed frequency is the speed, the relative speed divided by the wavelength. Right? Remember, the two are moving the same direction. That's why we subtract. And we replace the lambda here to get our equation. Right? So you can see that this one is now smaller. Right? We subtract, so the frequency becomes smaller. Okay. Okay, so the observed frequency or parent frequency. Okay, remember always that we are not looking at the speed of sound is always greater than the speed of the source. Right? We're not interested in the case where the speed of sound is less than the speed of source. Then you have short wave. That one you can read up from your book. Right? This is a parent frequency, F naught, or a parent frequency, observed frequency. Speed of sound is V. Sorry, or slightly up. It should be speed of observer. Sorry about that. There's a problem with cut and paste. Negative when the observer is moving away. Right? Remember, look at the direction. If the ask yourself, just this is the apparent frequency, observed frequency. Is a speed, V is the speed of sound. V0 is F is the frequency of source. V0 is the speed of observer. So we choose this one negative. Right? If we have this case there, right? Where the observer and the speed of sound are in the same direction. Right? In this case, would be the sound is going to the right, the observer is also going to the right. It's an example. So the frequency is larger. Sorry, what am I doing? Keep on making the same problem shorter. Sorry about that. Okay, let's combine the two equations and let's try to solve some problem. General equation. That's for the source that's moving. The observer is stationary. T is for the signal source is stationary. Observer is moving. Right? Combine these two. Right? Just replace this V by that one there. And then this one. Still the same. So this one is for both moving observer and moving source. V plus minus V0. Choose positive when direction of observer of sound and observer moving towards each other. Right? Moving towards each other or moving away from each other. Same thing. Choose positive. This one, the same thing. Right? For this bottom one. Choose positive when the direction of sound, look at direction of sound, and the source in opposite direction or moving away from each other. Either they are approaching each other, right? The speed of sound and the speed of the observer. Right? Sorry, the speed of the sound and the speed of the source are moving in opposite direction. Right? Choose positive. Right? Does this also happen in other? Right? Does it happen on sound only, or do we also see in light or electromagnetic radiation? Right? Doppler shift is observed with all waves, including sound and light. A moving observer will also produce Doppler effect. The formula for new frequency is different. Right? We have shown you just now how to derive the observed frequency. Light and other types of electromagnetic wave exhibit Doppler effect. An important application to astronomy where, for example, the velocity of distant galaxy can be determined from Doppler shift. Right? This is the Earth. Right? Where this is moving towards the observer, this side, the galaxy is rotating, moving towards the Earth there. Then it will shift towards the blue side. Right? That's why we call it blue shift. Whereas at this part there, right, where you don't see it moving, then we'll see the original wavelength. Or this one is moving, this part is moving away. So the light coming will tend to move towards the red end. That's why we call it red shift. Light from such galaxy is shifted towards lower frequency, indicating that galaxy are moving away from us. Right? Lower frequency means longer wavelength. This is called redshift, since red has the lowest frequency of visible light. The greater the frequency shift, the greater the velocity of recession, that means moving away. It is found that galaxies are moving from us faster they move away. Right? It's found that the further the galaxy are from us, the faster they are moving away. That's why they say this is evidence for Big Bang. Right? All the galaxies are moving away from us. As they are further away, they move faster away. So these are all the formulas we are expected to know how to use. Right? Summarize yourself. Use PowerPoint to summarize all the things, your own note. Make it yourself. Then you can remember. Okay, let's do some question. Let's go to checkpoint. I left you with one problem that I didn't solve yesterday. So let us solve that one first. Okay. Let's solve that one first. Today we left one question. I think it's 21.4. This one. Right? A tuning fork, 21/4, number one. A tuning fork is sound simultaneously with a guitar string, and the beat frequency is 5 Hz. Are heard when the guitar frequency is 425 Hz. If the guitar string is tightened a little, the beat frequency is 4 Hz. What is the frequency of the tuning fork? So of course, we don't know the frequency of tuning fork. We let it be F. Right? Tuning a tuning fork be F. So it can be F minus 4.25 or 4.25 minus F. That's why we put a modular sign there. We want the positive. Right? The net subtraction, the difference between these two is 5. You don't know which one, whether it's F minus 4.25 or 4.25 minus F. But there's this one telling you. Right? Frequency is speed divided by lambda. Okay. So when the string is tightened, what is happening? Tighten means you increase the tension, the speed, and thus the frequency of the note increases. Right? Tension increases, speed increases, wavelength still the same. Right? Frequency increases. So let us look at the new frequency is X. So we know it's X minus F equals to 4. Okay? So this one doesn't help us. It just tells us that X minus F, that's all, not F minus X. X minus F, F is greater frequency. So now we know from here, in this equation, right, that this is correct. F minus 425, not 425 minus F. Right? So when we tighten, we increase the frequency. Before that, the tuning fork frequency is greater than the guitar frequency. So take this one across there, 4.30 Hz. Can? This is more of reasoning. This one just give you reasoning, whether it's subtract or add. And then you decide whether you subtract or add here. Okay. Which comes first, 425 minus F or F minus 425? That's why you have to determine. Okay. If not, let's go and do some problem. Okay, 21.5, number one. A whistle that produces sound wave of frequency 512 Hertz. Before that, let me just give you some work to do for next Friday. Yeah, why is it not here? Okay, you should be able to go to checkpoint. Sorry, focus on STPM. Try at least multiple choice 1 to 15. Okay, you can do more, and then 1 to 5 for structure. Essay 1 and 2. Okay, is that clear? Objective.
Checkpoint.
Now we are doing checkpoint. So you should be able to do all the question already under your focus. So for next Friday, we will go over focus 1 to 15. And then structure 1 to 5. Write down. Essay 1 and 2. You want to do more? Go ahead. Right? Don't stop you. But we won't discuss everything since we won't have the time for that. Okay, let's try some exercise to make sure you know how to answer. You can try it out yourself. A whistle that produces, just using the formula only, a whistle that produces sound wave of frequency 512 is fixed to the rim of a horizontal wheel of radius 0.5 meter. The wheel rotates at 120 revolutions per minute. An observer stands at 25 meters from the wheel. Calculate the maximum and minimum frequency of the sound heard by the observer. Right? The whistle produces a frequency, and the whistle is attached to the wheel. Right? So one side of the wheel will move towards you, and the other side, after it moves towards you, it will move away from you. So we are required to find the maximum and minimum frequency. So how to find the speed? Is 2 pi r, that's the circumference, divided by your period. Right? Or 1 over t is f, frequency. This is a frequency. So you need to remember to change it to second. So 2 pi r, that's your radius. So we have to change to a new one in 10 minutes time. And frequency is 120 divided by 1 minute. 1 minute is 60 seconds. Okay, so calculate out. That's the speed of your moving wheel. Stationary observer. Remember, the observer is stationary. So we are using this formula. Right? To want the observer speed. This one. So maximum frequency we subtract. You choose the subtraction here. This one is largest. Subtract, put in your value. Right? Speed of sound. And that's your source, moving source. That's your moving source, Vs. Okay. So that one should be Vs rather than V. Sorry about that. Getting very careless. Okay, so Vs minus Vs is just that value. And then F, that's your F. Calculate out 522. Minimum frequency, this must be add lah. This is very straightforward. Okay, choose this one. Put in your value. This one is 330. This one is 6.28. And then that is your frequency, 512. So that's your answer. Okay, So you can either take the 5 minutes break, or you can use the 5 minutes to do the exercise. I'm not going to teach you anymore. After that, if we can finish the exercise, we will go to focus. We'll try some of the questions together. So that is my work for you while we have a 5 minutes break. Okay, anything to ask? Any question? Yep. Anything to ask? Any question? I have given you instruction to do already. Anything you want to ask?
Not sure.
Okay, now we will see you in 5 minutes time.
Okay.